So finally we get around to looking at the Ferguson Line Tamer, a power conditioner for 240 volt mains. Now, in the previous video I mentioned that I believe this thing contains a ferroresonant transformer, and that those, well, I classified them into two crude categories, which I've called relatively simple and complex and weird, and that I believe that this guy fell into the complex and weird category. So before investigating that, I wanted to try the relatively simple, which is this ferroresonant, which we examined the behaviour of in a previous video. So what are these two categories? Relatively simple looks like an ordinary transformer, a primary and a secondary, but a third winding with a capacitor in parallel to it. So this looks like a ordinary transformer, except that it's got this winding with the capacitor on it. What's not so obvious is that mechanically there's a magnetic shunt between the primaries and secondaries are always separately, they're not wound together on the core, they're separate windings, physically separated like that. There's a shunt with air gaps between them, which limits the ability of magnetic flux from the primary to get into the secondary, and also the secondary the flux can saturate the core, which is how it gets its constant voltage by not being able to be magnetised any more strongly, therefore the output voltage can't increase. Not shown here is that, well, if you look at this one, there's nearly always in the symbols these lines here which indicate that separation between the primary and the secondary, and the shunts and the air gaps are indicated by these lines. That really should look more like this, where the primary is above the lines and the secondaries are below. So that should be up there and the lines should be here. But that's relatively simple, isn't it? Okay, this thing's not super complex, this one, but it is different. It's got this compensating winding, it's got this neutralising winding. The compensating winding is on the same side of the air gaps and shunt as the primary, which is a bit strange, and the capacitor is across both those windings, and it's got this neutralising winding. And the reason I believe that this guy is of the complex and weird type is because its output says sine, and we saw in this one, for this one, that when it's at its operating point, its output is quite a square wave. So I suspect that all this other stuff, particularly this compensating winding, which can pick up sine waves out of the primary, presumably, does something towards making the output a sine wave. Now, I picked up this thing a couple of years ago just down the street during the hard rubbish collection. Luckily it wasn't that far because it weighs 25 kilograms. I never plugged it in or turned it on, and so before I actually do that, I thought we might do a Dave Jones and take it apart. So let's have a close look at it. Power goes in here, switch, and the tamed pixies come out here to this power point. Okay, so it seems to be made of two halves, which are U-shaped aluminium extrusions with fins all over them, so obviously needs a bit of cooling. Now, there's no screws anywhere except for these foots, so I'm hoping that undoing those gets this plate off, and hopefully the rest of it as well. Access to the rest of it. If worse comes to worse, I might have to lift this decal plate in case there's some screws underneath, but I'd prefer to avoid that, although I suppose I can't really because it covers the two halves, doesn't it? One thing that's immediately obvious is, although the feet are at that end, the weight is obviously more at this end. Seems a bit strange. You think you'd have the weight towards the base where it's closer to the floor, wouldn't you? Right. Potting. So looking inside, it's a little disappointing because everything has been potted, or rather the transformer has been potted, so we can't see much about its construction. We can't tell if it's the complex and weird type or the simple type really, but it would seem more like the simple type because the primary goes right over to there to that side and everything else comes out from a point in the middle of this side. If it was the complex and weird type, you'd expect something on the primary side, but who knows, it could well be happening underneath inside the potting. So I won't bother with a circuit, it's pretty straightforward. The mains comes in through a double pole switch to the primary. 2 wires come out of the potting to the ferroresonant capacitors. 2 more come out to a General Electric MOV varistor, 275 volts. And 2 more come out to the output sockets. And there's a cracked capacitor across the output. I recently had one just like that explode in an oscilloscope, so he needs to be replaced. Now I was concerned about whether or not this thing was isolated because there was continuity from the input pins here to the output pins on the socket. And taking this capacitor out, it's definitely cracked, so it has to be replaced. And if we look here, we can see that the earth goes to the neutral on the output, so that's what made it look like there was no isolation. So I might just disconnect that and see that the secondary is truly isolated from the primary, and then I wonder, what should I do? Should I leave that link out so that it is a true isolation transformer and it will be very well isolated, because being ferroresonant it will have the primary and secondary isolated physically, and then the potting on top of that gives further isolations, so it would make a very good isolation transformer. But if you're going to run appliances off it, then you should have the earth and neutral connected like this. Maybe I should have a switch for that, or maybe just stick a big warning sticker on it. Not sure. Anyone got any thoughts on that? I've replaced that capacitor and I've looped the earth back into itself so that the neutral and the earth are separate, and this is now a true isolation transformer. And maybe I'll slap a little note on there somewhere saying that, but it's probably only going to be me that uses it. But I should put a note there in case someone else ever gets it and relies on the earth there. Okay, let's see what it does when it's plugged in. The line tamer running off the output of the variac, and we're just going to monitor the voltage here. Turn things on, all the bloody switches. Okay, so it's drawing current already. 0.66 of an amp, which is at just 27 volts, so yeah. Oops, got to turn that one on, idiot. That's what we've come to find from Ferroresonance. They draw a lot of current with no load. 63 volts, 1.7 amps. Let's see if it's got a sweet spot. No, the current's going down. As we bring the voltage up, the current's going down. Under an amp now. So, yeah, the higher the voltage, the lower the current. Ain't that weird? Or, yeah, what's going on with RMS measurement or power factor in this thing? But let's stick in nominal 240. We're getting 247 out. I wasn't watching that as we wound up. So let's wind the voltage down now and see what happens to the volts over here. 247 with 240 going in. Drop it down to 200. Still 243, so yes, constant voltage output. Let's see where it goes below 240. 240 is at 153 going in. And if we take the minimum that 240 volts should be, which I think is supposed to be, well, 10% would be 216, is that right? Yes, so 216 volts output there. What input voltage we need to hit the minimum output that any 240 volt socket should be supplying. Look at that, 40 volts going in. Okay. Oops. Bit of hysteresis there. 216 volts with 40 volts going in. So how's that for constant voltage? Right, let's see if that holds true with a bit of load on the thing. Now I've also got my dummy load arrangement with the light globes, and I'll just keep the globes out of shot, but just for interest, we'll keep this meter visible and still watching the voltage on the other power point. Okay, so we're sticking 86 volts, 230 out there. Another thing I just noticed about this is compared to the other ferroresonant transformer, it's quite quiet. Okay, let's turn this on. I've got a shitty connection there. 87 volts, we're getting full brightness out of those bulbs up there. Doesn't matter what I stick in. Well, they get a little bit brighter because it goes up to 246 volts on the bulbs. So 287 volts going in. The bulbs are nice and bright, running off 250 volts, 61 watts. I can wind that right down. The bulbs are not noticeably dimming. Now they are, they're just starting to dim now. So around about there, it's 120 odd volts going in. We're still getting what appears to be full brightness coming out of them. Although it's got to be lower because it's less power and less volts. But yeah, 240 volts with 160 going in. That's pretty good, isn't it? Let's try it with an even bigger load. I'll stick this guy on there as well. So he's in parallel with those other bulbs. And again, I'll put it out of shot so it's not too much brightness. So to get 240 volts out again, I've got to stick in more like 190 now of this extra load. That's pretty impressive, that. It's fairly quiet. In fact, I can't hear any noise out of it at all. And let's have a look at the powers. 187 watts there, 297 here, so yeah. You wouldn't call that efficient, would you? Let's whack this up to 240 though, more typical input. 309 watts in, 200 out. Very inefficient. Let's see if there's a minimum power point. The power's only going up with more voltages. The power there, they seem to, the two powers seem to move in unison, so there's no optimum point where you can stick in a voltage here and get good power out there for a minimum power input. It seems to be lossy all across the range. Minimum of 216, which is the lower limit of 240 volt mains. 167 out for 270 in. So we're wasting a good 100 watts in there. And let's just turn this big bulb off again. Now we're getting 145, 54. So maybe the losses are constant 100 watts up to the limit of this, which is this thing is rated at 275 VA, so you can't put much more load on it than what I am. 200 watts out, surrounded watts in. Not very efficient, but I suppose now we should look at waveforms. But in terms of constant voltage, it certainly seems to be pretty good. Right, checking the output voltage, should be 245 here. Yep, between active and neutral on the output, between those and ground, 8 volts from active to ground, 45 from neutral to ground, so that's just capacitive coupling. So for the purpose of connecting to oscilloscope, I'll ground out the neutral. I'm reshooting this because, I don't know, the camera wasn't on or I've lost the footage or something, but I recorded this before but I can't find it. So what I'm trying to do here is look at the waveforms coming out of this Ferguson Line Tamer constant voltage line conditioner. Yeah, on the Grow here. We'll be doing it with various dummy loads, light bulbs here, and then plugging this one in will take us to the maximum VA limit of the Ferguson, and we use a variac to look at voltages, vary the input voltages, and see how the waveform changes on the oscilloscope. And down here on this thing we'll be able to see the power consumed by the dummy load. This here is a circuit I made up. It's just a voltage divider, 270k with a 27k tap, so it's a 1 to 10 divider, and we'll have the probe on times 10. The resistor here is 0.1 ohms. It's just between earth and neutral. Not really being used, but it pulls everything down to earth, so there's no problem with the oscilloscope having its grounded lead. That circuit, by the way, is basically this thing with the earth connected across to there. So we put the output of the transformer there and we measure it off on the oscilloscope there. 1/10 of 270 is 27k. Here we can see the incoming voltage to the Ferguson. Here's the output voltage on this meter and the waveform, and the dummy load globes are here behind that piece of paper to reduce the glare. So winding up the voltage, we're going to get at least 80 volts out before this meter starts working, so that's been met now. And the globes are on dimly. We're only getting 100 odd volts out. When this gets to 80 volts input though, around about here, suddenly the ferroresonant transformer is able to work with that 80 volts and go into its ferroresonant activity and give us a good mains output voltage of 226 volts. As we increase it further, if you watch the waveform, it's a good sine wave now, but as the voltage goes up, you see it's starting to round out. Not really a perfect sine wave anymore, but always pretty good. 200 volts in, 245 coming out, but the waveform's distinctly rounded now, and there's typical mains, 250 volts going in, 250 volts out. Take it further all the way to 286 in, 250 out, and a rounded waveform, and that's with a 30 watt and a 25 watt bulb, so 55 watt load. Now I'm going to wind it down and connect in this guy, which is 150 watts, so that'll take us to what's that, 205 watts, something like that, which is, and the transformer is rated at 275 VA, so we're getting close to its rated limit. So we'll see if the waveform's any worse with more load. So winding it up again. We've got to go more than 80 volts before we hit our resonant point, resonant transformer activity. Still more. Still only getting 130 out for 100 in this time. And there we hit it, 110 volts, and we're starting to get decent output. And the waveform's not bad. Winding up further. Bit of phase shift. That the scope's triggering at on line frequency, and you saw there's a bit of a shift, which is something ferroresonant transformers do. They shift the phase slightly. $200 volts going in, rounding, but yeah, and that's 286 going in. So that's pretty good. It's not a perfect sine wave, but it's, most things would be fooled by it. But for 250 in, 246 out, at its rated load efficiency, 300 going in, 200 coming out. Okay, so that is the Ferguson Mini Line Tamer. Keep an eye out for one in a rubbish collection near you. Catch you later.